And welcome back. So just now looking at moving on from Lewis structures and what we do when things are a little bit non-standard and how we go from there. So as we mentioned when we were talking about drawing Lewis dot diagrams, we can use dots or crosses to represent our Lewis dot diagrams. And typically we're trying to make it so that all atoms have 8 electrons to complete their octet. There are exceptions to this, and we talked about hydrogen. It only has 2 electrons in the first shell to complete its octet, so it has 2 rather than 8. There are another couple of exceptions that we alluded to in the previous video that we're going to look at in detail here. This is beryllium. Beryllium is actually a metal, and typically we would expect it to form ionic bonds, but in the case of BeCl2, it's actually covalent. And it's non-standard because we can see here that beryllium with its 2 electrons forms 2 covalent bonds. So it actually has 4 electrons in its valence shell when it's sharing, not the 8 for the full octet. So beryllium chloride or dichloride is our non-standard example. And also boron, as we can see here, boron trifluoride, BF3, okay, so boron trifluoride is actually a covalent molecule in which the boron is actually stable with 6 electrons in its octet. So it will only form 3 bonds. In this case, we can see that it forms 3 bonds with fluorine because fluorine only needs 1 electron each. We also see this with borane or borate BH3 also. So anytime boron is bonding with our halogens or hydrogen, we're going to see this B something 3 arrangement because it has 6 electrons in the valence shell and is stable this way. So just remembering that for our Lewis dot diagrams, we need the total number of valence electrons, add or remove electrons if it's charged, so adding electrons if it's negative, removing them if it's positive. Connect the atoms to the central atom with pairs of electrons, so this can be either lines or using a dot and a cross structure. Complete the octet, and then form double bonds if required to complete the octet. And don't forget that lone pairs, okay, remain in, so those non-bonded pairs. So if we move on from Lewis diagrams into what we call structural formulae, in this case, what we're doing is replacing each bonding pair of electrons with a line. So the lines are used to represent pairs of electrons in particular, okay? And then we arrange those in our molecule. So one line represents one pair, and we can see here that the bond has been replaced here. You can draw them this way. I recommend not to replace, so don't replace your lone pairs with lines, okay, your non-bonding pairs, just because it can actually make it a little bit more confusing when you come to look at molecular shape. So another way that we could actually draw this is Cl with the bond between it, and then our lone pairs just using our dots to represent the lone pairs. It just makes it a little bit clearer that this is in fact the bond between the two, rather than having the other lines around there. So if we look at things that have more than 2 shared electrons, so in double bonds, we can see that it has 6 valence electrons. It's going to form a double bond like we talked about in the previous video, and that each atom needs to share 2 electrons. So we will see a double covalent bond forming. So again, we can represent this with the double covalent bond, and we can place our non-bonding pairs as dots around it. Just a note on bond length. The more electron pairs that are involved in the covalent bond, the shorter the bond and the stronger the bond. So we can see essentially that we have more distance between the 2 atoms with a single bond, and it's easier to break than a double bond. We can see here that the distance here is greater than in a double, and then when we have a triple bond, we make it shorter again. We're pulling them closer together, and we're making that bond much stronger as well. If you consider it, we've got 3 points of connection here, 2 points of connection here, and 1 point of connection here. So our single bonds are much longer, and then as we increase another bond between the two atoms, we decrease the length and increase the strength. So as we do this, it's just because we're increasing the force pulling the two nuclei together. If you think about it, we have a lot of electron density in the middle of that two atoms now with all those shared electrons. So the nuclei are attracted more strongly to that cloud of electrons because the nuclei are positive and the electrons are negative. So just a reminder that we can have single, double, and triple bonds between molecules. Typically, we see single, double, and triple between carbon. It will form any one of these bonds between carbon atoms. We can also see single bonds between nitrogen in molecules such as this. We can see double bonds to nitrogen as well. Or we can actually see single bonds around nitrogen. So in this way here, remembering that nitrogen always likes to form 3 bonds and that it has a lone pair on the central nitrogen when it does form 3 bonds. Okay, so that's it for this video. Just a quick update on representing things using lines. The next video is going to go in about how we know what shape that we're talking about. So you'll notice here that I have drawn these ones in this kind of shape here where we're not drawing them flat, we're not drawing them like this. And that's what we're going to talk about in our next video, because in year 11, not only did we have to swap the dots for lines to create the structural formula, we need to be able to draw them with the correct bond angles around that central atom as well. And this is dependent on really where our electrons are positioned within the molecule. So I will see you in that video and in class.